that we're familiar with linear independence, let's explore some other options. Let's take a look at some special ways to determine linear independence. And by that I mean that I don't have to do the math. I don't have to do the row operations. Let's start by looking at just one vector. Well, if I have one vector, assuming that v is not equal to 0, then it's linearly, I think I forgot an L, linearly independent. And the reason for that is that if I took x1v equal to 0, assuming that v is not 0, the only solution is the trivial solution. So it only works if and only if v is not equal to 0. All right, what about if I have two or more vectors? Well, if I have 2 or 3 or a small number of vectors, I might just look at multiples. So we talked a little bit about this already, and we said that if one vector is multiple of another, then they are not independent. So let's say I have vector x, and vector x is 4, -2. And I have vector w, and vector w is 8, -4. And I have vector z, and vector z is 8, +4. Well, I can look at the set of xw, and because I can take 2 times x to get w, then w really isn't necessary because it's redundant. It's just 2 of a vector that I already have. So these are linearly dependent. Whereas if I'm looking at x and z, these are not multiples of one another. They're close, but obviously we have a difference in the sign there. And so these, not an equal sign, these are linearly independent because they are two separate vectors that I cannot get by multiplying one by some constant. The last way I can look at, again just by taking a look and not having to do work, is if a set contains more vectors than there are entries in each vector, then the set is linearly independent. And so I've sort of put the what does that mean, and that means there are more columns than rows. So before I look at a proof of that, let's just take a look at what I mean by that. If I have all 3 of these guys, because we didn't look at that in our last example. So if I was asking about x, w, z, well, x, w, z is in R2 because obviously there are 2 entries. But if I were to write this all together, 4, -2, 8, -4, 8, 4, well, I've got 3 columns, 2 rows. Then these are dependent. So let's take a look at a proof of that, and this is not a very formal proof. This is just kind of reasoning through. If A is the matrix of V1, V2, however many vectors I have, like I wrote here, then A is n by p. So those are the dimensions, n by p. Well, that is going to tell me that AX equals 0 corresponds to a system where there are n equations and p unknowns. N equations and p unknowns. And if p is greater than n, then there are more variables than equations, so there must be a free variable. So because there's a free variable, we know that means there's a non-trivial solution, and therefore they are dependent. There are 3 parts to this last question. I would like you to try all 3 parts on your own. When you are ready to check your work, press play. So the first question is actually fairly straightforward and easy because I can use one of my shortcuts. And the shortcut is that because I have just those 2 sets, all I have to do is look at whether they are multiples of one another. And we can see without doing any work at all that they are not in fact multiples of one another. I could take u times -6, and that would make that first entry the same, but the other entries would not be the same. So because these are not multiples of one another, yes, the first set is linearly independent. I'm going to skip over that middle one for just a moment because it's a little bit more difficult. Let's look at that last one, UVWZ. Well, we just talked about the theorem that says if you have more columns than rows, then it's linearly dependent. So if we look at UVWZ, we know that there are 3 entries in each vector. So I would end up with a 3 by 4, 3 rows, 4 columns vector. And obviously that's more columns than rows. So this one is linearly dependent. So the answer is, of course, no, they're not linearly independent. Let's go now back to the middle. And the middle question is not one that I can do by just examination. I actually have to do the math on this one. So here I'm actually going to create the augmented matrix. And again, would it be okay for me to leave off the augmented part of that matrix? Yes, it would be. I'm going to go ahead and write it this time. So I'm going to keep my first row exactly as it is. I'm going to take my first row times -2 and add it to my second row to give me 0, 14, -4, 0. And I'm going to take +2 times my middle row, row 2, to add to row 3. So 2 times 2 is 4, plus -4 is 0. 2 times 2 is 4, plus 3 is 7. 2 times -4 is -8, plus 0 is -8. And then I'm going to do a little bit more reduction. In the middle, I'm going to end up with 7 and -2, just by taking half of each of those. And then I'm going to take that new row and I'm going to take row 2 minus row 3. So 0 minus 0, 7 minus 7, -2 minus -8. And at this point I can stop because I can see that I have a pivot here and a pivot here and a pivot here. So do we have any free variables? No. So are the following sets linearly independent? Yes. So we've got a yes, we've got a yes, we've got a no.